works. I guess it.
Walter! Hey, buddy. Chris. Chris Piniche. Wow. I like it. What? That's not even how you say it. I know that. I'll show you. He's sitting with us. This is better than sitting next to him. Well, really, don't yeah, I heard about this. They're having the fucking annoying. And like small stuff. All the I was like, ask for I just had something. The more numbers you have.
Okay, we're live. Here we go. So it's recording and everything. Okay, so we'll start today with kind of a warm-up. This problem should be fairly straightforward. Well, you have to understand what's happening. So it's like a spool of wire, and it is like constrained against the wall, AB, and you pull on the rope with a force P, and they want to know how much will it take before the spool starts to spin and you pull the rope out. So you're like pulling the rope through the wall or something like this. So this one, it's straightforward in the sense that you only have one body. So you just draw a free body diagram of it. I will trace the circle. The dimensions here that are going to be important are the 3 and the 1 meter radii. So all right, so first of all, you have contact point B, contact point A. You have the center of the circle. So you have the tension, right, of the rope. We could put that acting somewhere down here, right? And then what are we going to have at our 2 contact points? A normal force. So you have a normal force at A, or this is B, and a normal force at A. And which way, if there were no friction, or if you pull hard enough, which way is this drum going to spin? Counterclockwise, right? So that means that the frictional forces have to oppose it. So they'll be the forces that would cause it to rotate clockwise. So you'll have a downward force at A and a leftward force at B. And what am I forgetting? Yes. Always say coordinate system. It's all right. You won't forget it then. What else? I'm missing a force. There's something really important I'm missing. The weight. I'm missing the weight. And then we probably should have some dimensions in here too. So we know that it's a 1 foot distance between the rope and the point A, and it is a 3 foot distance, so that's the radius. And yeah, I'm okay. We don't have to put units there. They're going to cancel out anyways because we'll multiply and divide by forces. I think that's it, right? Looks good? Okay. So let's just quickly kind of highlight our unknowns here. So we don't know NB, we don't know FB, we don't know NA, we don't know FA, and we don't know the tension. But we're told what the weight is. So that's 5 unknowns. But how many equations do we have? Or what equations do we have? We have the 3, right, for the rigid body. So sum of forces x, sum of forces y, sum of moments about some point, and we have 2 contact surfaces, right? And so for this thing to start to slip, it's not possible for it to slip at A and not at B, right? Not if it's spinning or rolling. So we get to use both contact surfaces applied, say, so what is the friction right at the moment where it starts to spin? We're given the coefficient of friction, and so we can write out that F of A is equal to mu S times NA, and F of B is equal to mu S times NB. And so we know we're in good shape because we have 5 equations, we have 5 unknowns. Let's just go ahead and start putting those together. So sum of forces in X is equal to 0 is going to be equal to what? We have the tension is the only force I think that goes to the right, and minus NA and minus FB. And I do recommend don't do the substitutions yet, right? Because otherwise, if you do make a mistake, it makes it almost impossible to figure out what you were trying to do. And we will always give the vast majority of the points for setting these equations up right, and only a little bit of points for solving them, generally. So we do the next one, sum of forces in Y and B. I'm kind of going through this quick because I'm hopeful that this is not, that new for you, minus FA, minus W, I think that's it. Where do we want to take our moments at? Well, the center knocks out NA and NB, and the weight.
Oh, might be. Wait, the center would do 3, right? Everything else would do 2.
The center does 3. Point B does 3.
Oh,
Yeah, okay, let's do the center. I don't have an, I guess we call that O. So the sum of the moments about the center point is going to be, so FB is going to make a negative moment, right? And really we ought to, if you don't write anything, we'll probably assume that you're doing this. That if you don't write the direction of a positive moment, we'll assume you're using kind of right-hand rule because I'm pointing up, but it's definitely nicer to tell us. So we have minus 3 FB. I'm not doing these in any particular order. Also minus 3 FA. And plus 1T. And am I missing anything? I think that's it. What's that? I think that's it. I think we're good, right? And so, let's see, is there anything hard here? So W is going to be 300 pounds. We're not multiplying by gravity because it's already a unit of force. We substitute in our NAs, and then our only unknowns are, we substitute in our FA and our FB, and our only unknowns are going to be NA, NB, and the tension. And we'll have 3 equations. And I'm not sure. Yeah, I think this one you'll probably want to use I'm sure you can solve a 3x3, but you might want to use your calculator, or you can do it by hand if you want. Okay? I think that's well enough set up. All right. So any questions about this one? I said it was just kind of a warm up. Okay. All right. So that was straightforward. So now this one is disappointing to me because it looks like it's really hard, and you set it up, and if you do it wrong, it's really, really hard. But if you do it right, it's really, really easy. So we'll do it right. So what do you think we should do here?
do both sides of the ladder.
Okay. You mean of either side, like
Yeah.
So 2 FBDs.
Yeah,
Okay. I'm lazy, so I don't want to do what I don't have to do. It turns out that is what you're going to have to do. Let's just talk through what would happen if we do different things, right? Yeah.
You said CB is a 2-force member.
Very good. So CB is a 2-force member. But so here's the super counterintuitive thing of this problem. is you're still going to want a free body diagram of CB. At least that's the easiest way that I've seen of how to solve this problem, right? So here's what you could do, right? So let's imagine you do a free body diagram of the whole thing, right? So if you do a free body diagram of the whole thing, what are the forces acting on that system? AX, AY, BX, BY. I would call those like, so for friction problems, I really like to rename those. So I'd call it like FA, FB for the friction forces, and NA, NB, but same what you just said. And then the guy, the weight. So you'd have 4 unknowns, and actually one additional unknown because you don't know the angle, right? And it's like, when I first looked at this problem, I thought, well, you know, I could take sum of moments at A and it would give me B. But it doesn't really give you the normal force at B. It gives you the normal force at B as a function of the angle. And that turns out to be kind of a red herring. It'll get you, at least it seems to me like that got me off track, okay? But there is something useful we can get out of that thinking. Which normal force is going to be bigger? A. Why did you say that? You're right. You're all right. Yeah, he's standing closer to that point, right? So you kind of intuitively know that if you're on a balance like this, the side that the weight is closer to, the weight is going to be more on. That means the normal force at A is bigger. And if the friction coefficient is the same, which side can support a lower friction force? Or higher friction force, whichever way. So if the normal force is higher at A, like its frictional force could be greater, right? But now, again, try to visualize that free body diagram of the whole thing. Maybe we should have just drawn it. What are the forces acting in X? Just the 2 frictions. So we know they have to be equal to each other, right? So what does that tell us? Which side is going to slip first? What's that? The right side, right? Because the left side can have the larger friction force because it has the normal force. So that tells us something already. We already know now that we'll say we're going to assume B slips. We'll check that assumption, but that will be right. Okay. All right, so let's start by drawing a free body diagram. And you could do either, or you could do both. But I'm going to show you how if you do CB, it makes your life simpler. All right, so there is, I guess I didn't really need to trace a line, but oh well. There is CB. And so what you said before was totally right. So this is a 2-force member, right? So we know that the force acting at C is going to be along the direction CB. Do you want to guess as to whether it's tension or compression? You should, it shouldn't even be a guess. You should be able to tell. It's got to be compression. Yeah. So we'll call this F, we'll call it BC. We'll worry about the directions in a sec. Now, if you just write FBC on the right-hand side, you've done nothing useful, right? Then FBC is equal to FBC and, you know, what do you do? It doesn't help. So what's much more helpful is to write on the right-hand side to break it into the components because those components have now more physical meaning, right? So we can write that there's a normal force at B and a friction force pointing which way? To the left, FB, right? And what we just said, because we're going to assume that it's going to slip at B, and we already kind of know that we're right in that assumption, we can write an equation between FB and NB relating those two, right? So let's now get the directions. So if this whole angle is theta, then this angle is theta over 2. And I planned that badly. That means that these are just opposite angles, so that's theta over 2 as well. Right? So we know that FBC is downward, and it's at an angle of theta over 2 to the y-axis, which we will label. Now, I'm not going to do sum of moments here, so I'm not going to write any dimensions in. And the reason why I'm not going to do any sum of moments here, you could think of it a couple different ways. So first of all, if I take sum of moments at B, it's pretty boring, right? It's just 0 is equal to 0 because FBC passes through point B, right? So that's not really helpful. And if I were to do sum of moments at C, it would give me a relationship between NB and FB, but I'm already going to have that relationship in the friction relationship. So I'm not going to write moments. How many unknowns are here? So we don't know the angle, we don't know FBC, we don't know NB, and we don't know FB. So there are 4. So you might think you need sum of moments, but let's just see what happens when we start writing these equations out. All right, so the first equation that we have is we know it's, so assuming B slips first, then we know that FB is equal to what? No, this is assuming it slips. Yeah, mu s, which is 0.3, or 3/10, times NB. Okay? And then we can do sum of forces in X. Is equal to 0. So the easy one is minus FB. Harder one is FBC times what? Sine of theta over 2. And the sum of forces in Y is equal to 0 is equal to NB minus FBC cos theta over 2. And what do you think you want to do next? Yeah, let's do that. So this equation is going to be equal to minus 3/10 NB plus FBC sine of theta over 2. Oops. And this equation is going to be NB minus FBC. I don't have to do anything there. Okay. And what do you want to do? Well, we can sub NB, right? Because we know we could sub it in from the second equation. So we know that NB has to be equal to this, right? From solving the second equation for NB. And so we write that in, and we're going to get, I'll move that 3/10 to the other side, so I'll have 3/10, and then the value of NB, which is FBC cos theta over 2. And then on the other side of the equation will be what we just had, FBC sine theta over 2. And some cool stuff happens, right? So we can get rid of the FBC. Just divide both sides by it. Cancel that out. And divide both sides by cosine. And what we get is 3/10 is equal to the tangent of theta over 2, which gives us a nice answer, right? So we can plug that in, and it's like 30-something degrees, I think. Any calculators here today? I'll have it in a sec. So theta over 2 is 16.7 degrees, but you got to multiply by 2. So theta is equal to 33.40 or so degrees. Okay? Are we done? If you wrote a really convincing argument, you might be able to be done. But really it's this thing, right? So right now we didn't really justify that. We talked about it, but we haven't written anything down. So the hand-wavy way to do it would be to say what we said before, that NA is going to be bigger than NB, so therefore their forces are going to be bigger. If you want to be a little more rigorous about this, now we draw the free body diagram on the other part. Right? So, okay, I don't need to trace a line. All right, so this is not the same angle, but that doesn't matter. So what are the forces acting on the left-hand side? Well, they're kind of the same, right? So we have NA, we have FA, and we're doing this partly because I want to show you how you want to write this. We have, remember we said it was compression FBC, which we don't yet know, because we canceled it out of the last expression. And we couldn't know it, because in the last, there's no weight in this equation, right? And FBC is obviously going to depend on the weight. So the first free body diagram we did was just kind of, it really was just geometry in the end. It had nothing to do with the forces, just their directions. So this one will give us that. And then, of course, we need to include the weight of the man standing on the ladder. So the angles are the same. So this is still theta over 2 to the vertical. And then it's another theta over 2 to the AC, right? Because it was theta between the two links. We're going to need this distance here, which was 0.25 meters. And then the length of the entire leg of the ladder was 2.5 meters. So 10 times more than this distance to the weight. I think that does it for dimensions. And we'll write out a coordinate system, so y is still up and x is still to the right. Okay, so what do we want to do now? What's that? Moments at A. Yeah, that seems like a good choice. That's going to give us FBC directly, right? So we'll take the moments at A are equal to 0. And turns out like this was a nice way to write it, right? Can you write out what is the moment caused by FBC? Are those perpendicular? Only if theta is equal to 90 degrees, right? So what you don't want to do here is you don't want to get like the x and y components of FBC and the x and y components of the distance. That's a lot of work that you don't need to do, right? So what is the equation that we need? So it's FBC times what? Remember, it's only going to be, let's write that. So FBC times 2.5. But what if theta is like 20 degrees? Theta is 33 degrees, right? So that this angle is really just like 66 degrees. That's not the right moment, right? That would have to be perpendicular. So what do you want to do to make that easier? There's 3 ways to compute moments. First way is you multiply the force by the perpendicular distance. Probably more than 3 ways, right? Second way is to do like Varignon's theorem, where you multiply the components of the force by the components of the distance. That's hard. And the third way, you multiply the force by the distance by the sine of the angle between the force and the distance. That's the one you want here, right? Do you remember? I mean, and you can kind of tell that it's going to work, because if this were 90 degrees, the sine of 90 would be 1, right? If this angle were 0, then this force would be lined up with that distance. Sine of 0 is 0, and it wouldn't generate a moment. So here you just want sine of theta, but we know theta, right? And then we got to get W. So W is going to make a positive or a negative moment. Negative, and its moment arm here is nice, just 0.25 times W. W is equal to, what is it, 75 kilograms? So it's 75 kilograms. That's a mass times 9.8 meters per second squared, so we got to fill that in. And so punching this all together, we have everything we need to solve for FBC. So 75 times 9.8, I won't write this down, it's 735. A quarter of that is 183. I'll divide that by 2.5, that's 73, and then I'll divide it by the sine of 33.4, and I get that FBC is equal to 133.5 newtons. I think that's right. I hope that's right. Oh, there's a mistake here. Right? This isn't 2.5, it was 0.25. So I think that makes this 10 times bigger.
Wait, no, but not that one.
What?
That one was right. The 0.25 was times the weight. But the length of the
Oh,
line-
yeah. No, you're right. So I think then we're probably okay. 133.5. Okay. So that seems good. All right. We kind of, yeah.
Oh, just to clarify with the FBC, like, basically you're saying that we only need to put in one angle because, like, if we split FBC into components, one component's going along the line, so like, the zero, is that what you're saying?
No. So that would be harder. So you'd have an x component multiplied by the y distance, and then you'd have a y component multiplied by the x distance. And neither of those would be zero.
Yeah.
But that's going to be the same as, remember, if you just have like a point O and a force acting this way, let's say, right? So you can either take the point at which these are perpendicular and do like r perpendicular times f, or if you want to do r, then it's r, let's call this theta, sine of theta times f, right? And from this picture, it kind of becomes obvious why, because r sine of theta is r perpendicular, right? So that's all we're doing. So moments are always like, you always want to make sure that you know the easy way to handle moments. Delete. Okay. All right, so we're that far. So I kind of forgot to tell you what we're doing, why we're doing this, right? So we already had the angle. That's what the problem was asking for. What we wanted to do is verify that we were right, that B slips. So how do we prove that that was right?
Didn't we talk about how FA has to be greater than
Not NA, yeah. But you're kind of on the, so we want to prove that if that's the angle, then FA had better be less than NA times the coefficient of friction. That's what we need to know, okay? So let's see how that goes. So to do the next thing, we need to do sum of forces, and since we're going to need to know both FA and NA, we'll have to do sum of forces in X and in Y. So let's do X first. So this is just FA minus FBC times sine theta over 2. Just be careful of the angles here. We need theta over 2 because that's the angle to the vertical. So that's 133.5 divided by the sine of 33.4 over 2. And so that, is that right? 33.4 over 2. Sine of that is like 0.28 divided. Okay, so FA is equal to, and I don't believe that. It says 460. That doesn't seem right. No, that's impossible. What did I do? Oh, I'm not dividing, I'm just multiplying. What am I doing? Yeah, so FA is equal to 38, right? Point. We don't even need a lot of precision here. You'll see why in a moment, right? So FA is equal to 38.4 newtons. Fine. We do sum of forces in Y. That's equal to 0. Same thing. So NA, now we have to have minus W plus FBC sine, cosine of theta over 2. Same story as before, so 133.5 times 33.4 divided by 2. The cosine of that, so that's 127 or so. And so what I need to subtract whatever W is, so 75 times 9.8. Should have written that down. So 735 minus 128 or so gives me that NA is equal to 607.1 newtons. Okay? And so what I just said, so FA needs to be less than mu s times NA, which means 38.4 needs to be less than 0. What is it? 0.3 or 0.2? 0.3 is the coefficient of friction, so 38 has to be less than 0.3 times 607.1, and you should see pretty quick that that's going to be the case. So multiply those out and you get 38.4 has to be less than 182 newtons. Right, so this means that the frictional force that it takes to hold point A in place is 38.4, and the maximum frictional force that we could apply is mu s times NA is 182. So it's clearly less, and so therefore B will slip before A. The only thing we hadn't done yet is we didn't calculate like the force at B. Although that's really easy. If you look back to your free body diagram, it's just going to be the sine of theta over 2 times FBC, right? And we didn't calculate NB. But if you go ahead and do that, you'll get that NB times 0.3 is equal to FB. We got that from here, but we did it without even knowing what FBC was, because we didn't need to. We know the relationship between those two, just from the geometry. Okay? Any questions? Oh, we went really fast today. That's all I had. So if you have any other questions, if you were looking at the homework and having problems, we could look at them. Otherwise, we could just get out of here, because it's Friday afternoon. Oh, the car one's hard.
Yeah, we did that on the recitation. Well, we did the free body.
Okay. So the problem with some of these is they take a little bit of, I don't want to say luck, but if you do them the wrong way, they're hard. And if you do them the right way, they're quite easy. Well, they can be easy. So this is without any advanced prep. Hopefully, why this doesn't work for me. All right, so there's the car problem. And let's see here. So, well, the good thing about this problem, there's only one body. So the free body diagram is sort of obvious. I'm sure when I trace this, it's not going to look like a car anymore. But that doesn't matter. In fact, I'm just going to cut it off there. We did have a student who drew beautiful, beautiful free body diagrams and never finished his problems. And we're like, it doesn't really matter. Okay, so there's the car. So it has a center of gravity here. So we need to draw the weight. And, okay, I kind of remember how this goes now. So, what else do we need to know? If the coefficient of friction. Always look at this problem and I think to myself, oh, you got to consider, it must be going around a corner, so you'll have some centrifugal force. No, it doesn't have that. All right, so which way are the friction forces going to point? To the right. And okay. And here you can kind of cheat. So should I draw a friction force at A and at B? So the reason why I don't have to is because how do I want to do this? They have the same line of action, right? And in the case where it tips, actually then all the weight is going to be on wheel A. So then there won't be a friction force at B. And the case where it slips, so NA plus NB is going to have to be equal to the component of W that's along the direction that's perpendicular to the slope. And so, yeah, I think we can write it this way. So I think we can write that FA is equal to NA. Well, that's not, we can't really write that. We have to write FA is less than or equal to NA times mu. I wrote that backwards. And FB is less than or equal to NB times mu. And so FA plus FB has to be less than or equal to mu and the sum of the normal forces. And so what we can do is we can just call this thing F. So we can say we'll have a frictional force acting in that direction. And really, you can think of it, it might be two forces, but we don't care. They'll add together because they have to be along the same direction, right? And we have to consider two cases. We have to consider the case in which it tips and the case in which it slips, right? And I think it's easier to look at the case in which it tips first, because we'll have fewer forces. So when it tips, right, when it tips, wheel B is going to lift off, right, which means there would be no force here. You can think of it as the same way as saying if this were just a box in total contact, then the overall normal force would be acting all the way out here. So we're going to put all the weight here, NA. And let's see, I think that's all we need. And we're not given the width of the tires, are we? I don't think so. No. So we assume that's like negligible. We assume the weight will still be at the center, the normal force will still be at the center of the tire. In reality, it would probably be out a little bit more, but that's going to be negligible here. So the important thing is it's 5 feet between like the part of the tires in contact. All right, and we also need, okay. So let's see, what do we want to do here? Now we have some geometry to worry about. So if if the surface is an angle theta from the horizontal, then the friction force, which is perpendicular, oh no, I'm sorry, the friction force is the same direction. So it is going to be an angle theta from because it's along the surface. And NA will be at theta from the vertical. And both of these are going through some point A. And this is going through point G. Did I tell us, or I guess we just assume point G is in the center. Oh yeah, it says in the, so I assume we assume that G is going to be 2.5 from the side. It's in the middle of the car. That actually might not be true for some cars, depending on where the engine's mounted, but again, we don't know, so that's what it's going to be. So we know that this distance is 2.5, and this distance is 2.5. And I guess that's good enough. And I think we probably want to set our coordinate system with the slope, because the only force that's not that way is W. I think that'll make our moment. And our moment arm's already set up this way too, so let's do that. So we'll do X and Y. Okay, so what am I missing here? if I take moments at A, did I? If I take moments at A, then how do we not slide or tip? You see the problem here?
This is the tipping case though, right?
Yeah.
Assuming it does too.
No, but I mean, if I take moments today, I'm only just going to have W times something. So I can think of one thing, but I'm not sure it's right. Is it just when G is directly above A? I think that might be the case. Yeah, that's all there is to it, right? So as I drew it at a specific angle, right? But if you imagine rotating this, at some point G will be directly above A, and that's the point it would tip over. Yeah, and as long as the car's not going around a curve and there's no centrifugal force pushing it into the wall, then that's all there is. So, yeah, I told you I didn't look at this. All right, so car will tip when G is directly above A. And above we have to be careful, not in terms of Y, but in terms of this vertical direction, in terms of the, right, when the line of action of W goes through both A and G. That's about what we say, right? So how are we going to write that equation? I think we'd be best off just to draw the points. So this is point A, here's point G, and here is, let's do the slope that way. So this is 2.5. This is also 2.5. And how do I get this to work? So I can calculate that angle, right? The angle between, so point B is out here somewhere. So the angle between GAB, I can calculate pretty easy. In fact, I think it's just 2.5 and 2.5, so isn't it just 45 degrees? Yeah. And when GA is straight up and down, or 90 degrees from the horizontal. So what this tells us is when theta is 45 degrees, right? Theta is 45 degrees and beta is 45 degrees, then this line becomes vertical, because this line's horizontal, right? So I'm not drawing this super well. So beta equals 45. So when this is 45 degrees, car tips. Okay, so that was the first case. That was a bit painful. And for the second case, now what we're going to look at is we can just, in the second case, we don't have to consider sum of moments, and we can just consider sum of forces, right? Hopefully you can pretty this up. So this is case 1, case 2. So car slides, car slips. So in case 2, let's see, do we want to do, yeah, let me just, Why isn't this working? I'm trying to make a copy. Didn't have to draw this again. Oh, keyboard. This isn't a wireless keyboard. That's why. Oh. Copy. Paste. There it goes. Okay. So here's our free body diagram for case B. So for case 2. So for case 2, the car slips. And so I'm not going to try to be so clever here. So what I'm going to do is hopefully my computer starts working again. There it goes. Is in this case, we will have an NB, and we will have an FB, and an FA. And so in this case, but I'm not going to write the directions of these, because NB is in the same direction as NA, and FA is in the same direction as FB. Okay? So in this case, we only need sum of moments. Wow, this thing is like just not happy with me today. It's not going to let me change color. All right, I guess we're red. Okay, so in this case, what I'm going to do is we're not going to take sum of moments because it's not tipping, and the reason why we're not going to take it is because we don't know the balance of NA and NB. We don't care. Right? What we know is that the sum of forces in Y is going to be equal to, and note the coordinate system here, NA plus NB, and we're just going to call that like a thing. Those are that's the total normal force coming out of the tires. And it's acting in the same direction. Minus, and here we do need oh, I can't change that either. All right, whatever. So here, sorry about the colors here. So this angle is what? It's theta. And the way you can think of this is if theta were 0, then this would be 0, right? So this angle is also theta. So it's going to be times W or minus W cos theta. And that has to be equal to 0. And our sum of forces in X is going to be FA plus FB minus W sine theta is equal to 0. And then what we can say is that when it slips, that FA is equal to mu S NA, and FB is equal to mu S NB. And this is what I was trying to allude to before, and it helps to have the equations in front of you, is I can just add these two equations together, and I get FA plus FB is equal to mu S NA plus NB. And that's what I'm going to substitute in, right? So I'll just substitute for FA plus FB right there. And so I get mu S, oops, not that, NA plus NB is equal to W sine of theta. But NA plus NB from this equation is equal to W cosine of theta. So plugging that in, so I get mu S is equal to W cos theta. I'll divide both sides by that. So I get W sine theta divided by W cos theta. And I just get that mu S is equal to tangent of theta. And it's 0.3, right? So the arc tangent of 0.3, it is 0.3, isn't it? Oh no, 0.4. So the arc tangent of 0.4 is equal to 21.8 degrees. All right, so what does that tell us? That tells us that when the slope is 21.8 degrees, the car is going to slide down the slope. But when it's 45 degrees, it's going to tip over. So what's going to happen? It's going to slip way before it tips. All right, so that was a bit sloppy, but we got there. Okay? So a really good approach to solving these problems, and depends on what where you guys live and what you can do, but like if you're on campus and you know people on campus, like do these things on a whiteboard and just make a big mess of it. And then once you figure it out, copy it onto a sheet of paper, but then you can kind of clean things up. Yeah, that's how I write solutions too. Like when, like all the exams and all the quizzes and all those solutions that posted, they're not always like pretty the first time around. Usually I rewrite them, redraw things, and take my time because like, you know, that's if those solutions are a complete mess, then we get a lot more regrade requests, and life gets harder for us. So yeah, so it's often helpful to do that. Now on a test or a quiz, you just do what you can, and we'll do what we can to understand what you write. But yeah, this problem is, the more you think about it, I think that the sort of easier it gets, but it's kind of deceptive at first. I remember it being tricky. The problem is, if I teach the class every year, I forget how to solve it for the next year. So, all right, so I think we're in pretty good shape now. It's 15 minutes, I'm getting tired. So, any other questions? I think you've had most of your homework problems seen. Okay, let's stop recording.